Thank you so much for the introduction. Also, I would like to thank the workshop organizers for the opportunity to speak here today, as well to the entire team of program organizers. It's been a pleasure to participate in its activities. So what I'm speaking today about is validated numeric techniques for singular integral operators. And the message that I want to get across is that techniques originating in harmonic analysis, partial differential equations, and validated numerics, make for a very fertile and effective mix. So the examples that I'm going to bring here today are going to, it's work done over many years with many collaborators, and it has, it's a team that has a deep and rich history. But I just want to show how the techniques that I'm going to be covering, are effective in improving spectral properties of singular integral operators that are relevant for establishing well-posedness of elliptic boundary value problem in non-smooth domains. I've seen many talks here talking about corners, cracks, so domains with irregular boundaries are something very much of interest, and how these techniques allow us to establish sharpness of well-posedness results. The numerical simulations conducted in, for this type of problem are also a source of inspiration for theoretical results that hold actually in a much more general setting. So to get started, let me start with a very basic boundary value problem for the Laplacian in the upper half space. So let's consider the Dirichlet problem for the Laplacian with LP data in the upper half space. I would like to mention from the very outset that the nature of the problem is not only affected by the function space in which the data lies, in this situation LP, but rather also by the manner in which the size of the solution is measured and by the manner in which the trace is taken. Throughout this talk, the size of the solution is measured in terms of the non-tangential maximal operator, and the trace of the boundary is taken in non-tangential sense. This is very natural from the point of view of harmonic analysis theory of Hardy spaces of holomorphic functions, Fatou theorems, Calderon-Zygmunt theory. So let me just explain a little bit how this goes. If we're in Rn plus, then the boundary naturally identifies with Rn minus 1. And for a point x on the boundary of the domain, we're going to consider gamma of x, the non-tangential region with vertex at x, of some fixed aperture. Then the non-tangential maximal operator of a function u defined in the upper half space at a point x on the boundary is the supremum of absolute value of u taken over the non-tangential region generated by the point x. And the non-tangential limit at the boundary is the limit as the point yt approaches x, but limited by the fact that yt needs to be within the non-tangential region generated by the point x. So, this particular problem is many times, the starting point for a graduate course in first year graduate course in harmonic analysis, and we teach our students that this problem is well posed, there exists and there is a unique solution for this problem, namely the solution is nothing else but the Poisson convolution with the boundary data f. And there is a rich harmonic analysis which allows us to establish non-tangential maximal function estimates of the solution in terms of the boundary data. So what I'm going to be interested in is look at this type of problem in more general domains. I'm here, I have a litany of type of domains that we may consider. We're starting with, very smooth C1, C infinity, C1. We're looking at domains that have outward uninormal vectors with vanishing mean oscillations. We're looking at Lipschitz domains, infinitely many singularities possibly accumulating, and we're maybe crossing in the realm of geometric measure theory, where the domain is so rough that its boundary is not even locally the graph of a function, but it has enough structure that you have a rich harmonic analysis, and Calderon-Zygmunt theory still holds. So, that's the type of domain, that I have in mind. Think about, the upper graph of the Weierstrass-Nowhere differentiable function. So like ideally to be able to solve elliptic boundary value problem in domains that are very, very rough. Because in reality, even something that looks smooth when looked upon carefully actually exhibits irregularities and of a very intricate nature. So that's what I have in mind. So I'm going to try to move from the upper half space to more general domains. So I'm going to consider here omega an open set, bounded and reasonable for the point of view. For the moment, let me leave this vague, and fix an integrability index P between 1 and infinity. Then the Dirichlet problem associated with the Laplacian with LP data has 3 parts. It has the PDE condition. We're looking for a harmonic function in the domain omega. It has a boundary condition. We're looking for the non-tangential trace of the function u at the boundary to match the Dirichlet data f, which is assumed to be in LP. And it has a size condition. As I said, the type of problems that we're looking at come accompanied with the requirement that the non-tangential maximal function of the solution is in LP. So now we're no longer in the upper half space, so the non-tangential region is no longer necessarily going to be a straight upright cone, as we've seen, but the spirit of it, is the same. So here is, how one defines the non-tangential region associated with a point on the boundary. It consists of points y in the domain omega such that the distance between x minus y is controlled by a multiplicative factor of the distance between y and the boundary, and this should have been a capital Y. So in other words, you cannot be close to the boundary without being close to the point that generated that particular non-tangential region. So we're taking non-tangential limit at the boundary, much like we've done in the upper half space, by taking limits within these non-tangential regions. So in order to address the PDE question, the question is, how do we generate lots of harmonic functions? If we are in 2 dimensions, a mechanism capable of generating lots of harmonic functions, we've seen here over and over again, this week, is through the means of the Cauchy integral operator. So which I've written up here. So here Z is a point in the domain omega, and G is a reasonable function, nice function defined on the boundary of the domain omega. And because of the holomorphicity built in the kernel, this is a holomorphic function in the domain omega. We're going to take the real part in order to get to a harmonic function. And let's assume that G is actually real valued. So I'm going to take the real part of this expression, and based on the fact that this zeta is nothing else but I multiplied by the outward duty normal vector, this sigma, where sigma now stands for the surface measure. When we're taking the real part here, I've normalized the denominator. I multiplied top and bottom by the conjugate. I replace here this zeta by I nu this sigma. The I cancel the contribution from 1 over 2 pi I here, so we're left just with 1 over 2 pi. And now G is real valued. This is a real quantity. Sigma, is real valued. It turns out that the real part of this product of complex numbers, when regarded as vectors in R2, is nothing else but the scalar product between nu and z minus zeta. Here, nu stands for, I should have said earlier, nu stands for the outward duty normal vector to the boundary of the domain omega. So that's a good candidate, that's a good machinery to generate lots of harmonic functions. So, I'm sure that, many of you recognize here the classical harmonic double layer potential operator. So, which, in 2 dimensions, it comes, naturally by taking the real part of the Cauchy integral operator. So in n dimensions, we're taking something very similar. We're just, adjusting, 1 over 2 pi to an appropriate dimensional constant. And instead of having a square here, we're going to put the dimension of the Euclidean space n. it turns out that this indeed is a very good mechanism for generating a lot of harmonic functions. So, the kernel here is nothing else but the normal derivative of the fundamental solution of the Laplacian. Here E stands for the classical radially symmetric fundamental solution of the Laplacian in Rn. And because when we take the Laplacian and the variable x, this, hits the fundamental solution E. X is in the domain while y lies on the boundary. This is going to be, formally 0, right? So this is indeed a harmonic function. A very powerful, mathematical theory, under, titled Calderon-Zygmunt theory, gives you that the non-tangential maximal function of the double layer potential of G is in LP whenever the density G was originally in LP, and one has uniform estimates for any p strictly between 1 and infinity. So if you think about the original PDE, I'm going to seek its solution as a double layer for some G at the moment unspecified. But the PDE is satisfied because the double layer is harmonic, and the size condition is satisfied because I started with G in LP. So at the, all that remains to be done is to have the boundary conditions satisfied. So in fact, what we've done here is to walk through the steps of reducing the entire elliptic boundary value problem to a boundary integral equation, which is the essence of the layer potential method for treating elliptic boundary value problems. So when we take the non-tangential limit of the double layer at the boundary, one obtains 1/2 identity plus kg, sigma almost everywhere on the boundary, where k is the boundary-to-boundary version of the double layer potential operator. So if you look here, and I have an error, actually, I see it now, I should have had 1 over omega n minus 1 here as well. So it's precisely this expression with the fundamental difference now, though that x is on the boundary and the integral has to be understood in the principal value sense, because now x, y can be equal to x. So we have a singular kernel. So, so the boundary now is, the boundary value of our candidate for solution is 1/2 identity plus kg. So as long as we match that with the Dirichlet data F, we solve the problem. So it is really desirable to establish invertibility properties for 1/2 identity plus k, and on LP spaces, and to phrase this as a spectral problem, this amounts to saying that -1/2 does not belong to the spectrum of the operator k on LP. Here the spectrum consists of all those points z in the complex plane such that z identity minus k is not invertible, okay? So I want to say that, before I move on to some concrete results, I want to say here that the layer potential method has one big advantage versus other types of approaches, in the sense that it does not in principle distinguish between the Dirichlet problem, the Neumann problem, the transmission problem. The blueprint is the same. And it does not distinguish in principle between the case of a single equation and that of a system. So methods that's the case, for instance, for methods that rely on the maximum principle, but the layer potential method does not have that particular problem. So just to illustrate this point, for the Neumann problem, the boundary integral equation that needs to be solved turns out to be -1/2 identity plus k star, where k star is the formal adjoint of the operator k that we've seen before. So in a way, if we know the spectrum of k, we understand by duality the spectrum of k star. So what you do for one operator, it's essentially, out of it you can read a lot more. So in principle, once you know how to solve a problem, you know how to solve others as well. So in this situation, it's important to show that 1/2 is not in the spectrum of k star acting on LP. And something similar can be said for transmission problems. Imagine a bounded domain omega and trying to find harmonic functions u plus and u minus in omega plus with an appropriate size condition such that the traces coming from inside and outside match. And this is, the transmission condition for the normal derivatives that involve some given coefficient gamma. if you try to solve this via boundary integral methods, the boundary integral equation that you obtain is this one. So you can phrase this as a spectral question. You are able to invert this operator whenever 1 plus gamma over 2 times 1 minus gamma is not in the spectrum of the operator K star when acting on LP. So let me mention a few historical facts here. If the domain omega is bounded, the smooth K happens to be a compact operator on LP, and as such, 1/2 identity plus K becomes a compact perturbation of an invertible operator, which makes the operator Fredholm with index 0 very close in spirit to the invertibility condition 1/6. So, however, the presence of a single corner prevents K from being compact. So, in fact, the very boundness of the operator at the level of LP, in the case when the domain omega is Lipschitz, is a very hard problem. This has been solved, you know, after an original development by Alberto Calderon for the Cauchy integral operator on Lipschitz curves with small Lipschitz constants. The problem has been completely solved by Koifman, McIntosh, Meyer in the early 80s by showing that if the domain omega is Lipschitz, then K is bounded on LP for any P strictly between 1 and infinity. So, however, K is no longer compact, so then the Fredholm alternative no longer functions if the domain omega is Lipschitz. But invertibility on L2 is known due to Greg Verkota in mid-80s, and actually much more is known nowadays. If the domain omega is Lipschitz, then the operator 1/2 identity plus K is invertible on LP for any P between 2 minus epsilon and infinity, and this is sharp in the class of Lipschitz domains, in the sense that if you give an integrability index P that is strictly less than 2, one can construct a Lipschitz domain for which the invertibility of 1/2 identity plus K fails on that particular LP space. So, you know, in order to transition to some numerics, I want to say here that, you know, the numerical treatment for solving the integral equation 1/2 identity plus Kg is facilitated by having the knowledge that the spectral radius of the operator K on LP is strictly less than 1/2. And in fact, this is actually an open problem in the case of in the class of Lipschitz domains, even for the Laplacian. So here rho stands for the spectral radius of the operator K on LP, and this is conjectured to be less than 1/2 for any P between 2 minus epsilon and infinity. This has been, you know, it's a problem in one of Koenig's books, and it's, you know, a problem opened also brought up by Greg Verkota. The significance of having a spectral radius which is less than 1/2 for the operator is that you can then express the inverse as a convergent Neumann series. And then going back to the solution, it gives you a way, an explicit way of obtaining the solution of the original boundary value problem. So we're going to be interested in some spectral issues. So I want to, you know, I'm going to be very brief about the history, but, you know, the history is, you know, long and distinguished. Neumann himself has been looking at issues like this. Certain things have been done in the case of planar domains of bounded rotation without cusps by Radon. Here S stands for essential spectrum, the set of points for which Fredholmness fails for the operator Z identity minus K. Shelepov has spectral radius formulas for K on LP if the domain happens to be piecewise C1. Things are known about the point spectrum on L2. The point spectrum eigenvalues are always real and always between -1/2 and 1/2. And more things are known about convex domains, about the point spectrum. Achner has shown some really nice examples showing that the entire range -1/2 to 1/2 for the point spectrum is sharp, so everything is in there, and that the very spectral nature of a single point can change within the domain. A point may be in the essential spectrum, or maybe in the continuous spectrum, but not in the essential spectrum should you change the domain, all right? So it's a problem that is very sensitive both to the analysis and to the geometry. So let me show you some concrete examples. We're looking here at the spectrum of the Laplace operator on an infinite sector of angle pi over 5. Here the spectrum is the red curve that we're looking at. So every point on the red curve is a point where z identity minus k fails to be invertible. In fact, in the situation of a sector, the entire spectrum is an essential spectrum. It's Fredholmness that fails in this setting. Okay? Anything else, you know, should we take a point in here, then that's actually a point in the resolvent. So that's how the spectrum of the Laplacian looks like. We're looking here at multiple spectra. I just want to show you, you know, we're varying this from pi over 5, which is the red curve, which is the longest, to 4 pi over 5, or if you want 5 pi over 5, which is simply the origin. I just wanted to emphasize that the length of the curve, the spectral radius, which is the radius of the smallest disk center, that the origin which contains the spectrum, you know, changes with the angle of the sector. The more acute your angle is, the larger your spectral radius is. Okay. So this is, you know, L2 versus L3 now, and now I have 15, you know, spectra plotted on the same line. But let me look here at the spectral behavior of the spectral radius with respect to the angle in radians. The more acute the angle is, the larger the spectral radius is. And look also at the behavior of the spectral radius versus the integrability exponent. P equals 2 tends to be the worst case scenario. The spectral radius is the largest. Okay. All right. So I'm going to show a few examples. I have just a few pictures on the case of the Lamé system. So here is the Lamé system of elastostatics, and what I want to point out, you know, maybe not in contrast, but certainly maybe some people are not aware, for the Lamé system of elastostatics, there are infinitely many double layer potential operators that one can consider, because there are infinitely many ways of writing the system as A, I, J, alpha, beta, partial I, partial J, with summation over repeated indices. Okay. So new collections of AIs lead to a new operator. You know, these are, you know, we're looking here at an infinite family of coefficients that give type to give rise to the Lamé system. I'm going to choose a very particular one that gives rise to a layer potential that has most in common with what we've seen in the case of the Laplace operator. And this is how the picture changes in the case of a single angle, of a single sector. Now we have two curves, okay? And let me also do a curvilinear polygon. So imagine that I have two angles, pi over 10 and 5 pi over 6, and I smooth this jointly as to not introduce any other singularities. Now the picture changes in the following sense. You know, I have two pairs of curves coming from pi over 10. These are the longer ones. Then 5 pi over 6, the blue ones. And now the spectrum consists of everything enclosed by these curves. And we can actually pinpoint what's the Fredholm index in, you know, various regions determined by these curves. I only wanna. I realize. Let me get to the computer-aided results now. You know, the computer-aided results are a part of a comprehensive program on studying spectral properties of singular integral operators, which I've done jointly with some of my former graduate students and Warwick Tucker, now at Uppsala University, and some of his students. And it spans, you know, many years. We have both positive and negative results. And these are, you know, results that are a mix of analytical and numerical approaches. So the traction problem for the Lamé system, it's a different one that I've showed before. So this, the singular integral operator is different. It has, this is what its spectrum is. And here is a here is a result. Okay, the numerical evidence suggests that the spectral radius has a particular formula that depends on the angle, that depends on the integrability index, that depends on the a particular combination of the Lamé moduli that appear in the writing of the system. And that's what the spectral formula should be. And in collaboration with Tucker, we have shown that if the angle spans the interval from 0 to 2 pi, but is not really, all the way to 0 and not really all the way to 2 pi, so just a little bit inside, and p is between 1 and infinity, then the spectral radius is between this conjecture value and the small error. Okay? So, the point is that, if I go here a little bit more inside, I can make here the error much smaller, and so there are, this is a, I just want to give this example as a flavor. So this in particular allows you to identify a range of theta, kappas, and p's for which the spectral radius conjecture is valid. Let me also give you a negative result. We have been able to identify a second-order elliptic system which is symmetric and strongly elliptic, such that the spectral radius conjecture does not hold. It was believed that maybe, this type of conjecture that we've seen for the case of the Laplacian extends for other, second-order elliptic systems of this type. So here we're looking at the spectrum of that particular operator. My last point that I want to make here, and this is inspired by some numerical simulations that I've done a while ago with Toby Driscoll at Delaware. If the domain is in 2 dimensions and can be very general, this is bounded uniformly rectifiable domain. Think about some sort of bounded, a truncated version of that upper graph of the nowhere differentiable Weierstrass function. Then the spectrum, the essential spectrum, and the point spectrum of the double layer potential associated with the Laplacian is symmetric with respect to the origin, which has been inspired by the numerical simulations that we've seen. With this, I would like to thank you for your attention.
Could you give some details how the computer-assisted proof works?
Yes. So I was running out of time, so I'm just gonna, briefly point out to the following. This is how, the key step in this entire analysis. The fact is that when you're on so the idea is that if I have a curvilinear polygon via an appropriate localization, I can reduce matter analyzing, what happens in an infinite sector by taking the tangents at the vertex, at the point where the two piecewise C1 smooth functions join. On the sector, one can obtain an explicit description of the spectrum. This is because in this particular geometry, the operators in question turn out to be of Mellin convolution type. This is some sort of Fourier transform with respect to the Haar group, and because on the Mellin side, the operator KF looks like it looks like multiplication by the Mellin transform of the kernel of K. Then the spectrum becomes the collection of all Z's for which the determinant of this Mellin symbol vanishes. At the point 1 over P plus IY. P is the integrability index, and Y is things become very, very explicit. We get here a particular equation which is very explicit. It involves trigonometric functions typically, and so you get an explicit description of your spectrum as a parametric curve depending on Y. And many times, in order to show that the spectral, let's say that I would like to show that the spectrum is in the unit disk, I can do the parameter Y varies between negative infinity and plus infinity, and via analytical methods, I can take care of what happens as y is large. The delicate part we've seen, that happens, when essentially the spectrum hits the real axis. That's essentially, corresponds to y being equal to 0. There is the most delicate part. This is where the points in the spectrum have the largest absolute value. And this is handled numerically, and it involves interval analysis. So this is now the problem is reduced to a compact set to show that the values of a function, of an explicit function over a given compact set, stay away from 0. And this is something that is within the expertise of Warwick Tucker. This is the way the numerical implementation is done is in such a way that the result is rigorously guaranteed. It takes into account the round of errors and all these things. So this is a genuine computed-aided proof.
Any more questions? Okay, well, let's thank Irina again and also thank all our speakers.